Voyager 1 is currently traveling at 17 kilometers per second, or 38,000 miles per hour, heading toward a star system it will not reach for 40,000 years. This is not just a journey of distance, but a journey through deep time. Launched in 1977, this spacecraft has surpassed all original engineering expectations, becoming the farthest human-made object in existence. As of 2026, Voyager 1 is located over 24 billion kilometers, or 15 billion miles from Earth. At this immense distance, a radio signal traveling at the speed of light takes more than 22 hours to reach the probe, and another 22 hours to return. The sheer scale of this communication delay highlights the profound isolation of the spacecraft. It is currently navigating the interstellar medium, a vast and complex region of space that exists between the stars. This environment is not empty, but is filled with a tenuous plasma, cosmic dust, and interstellar magnetic fields. The data returned by Voyager 1 has fundamentally altered our understanding of the boundary between our solar system and the rest of the Milky Way galaxy. To understand the future of Voyager 1, we must first examine the boundary it has already crossed. For decades, the probe traveled through the heliosphere, a massive protective bubble created by the solar wind. The solar wind consists of charged particles streaming outward from the sun at speeds of 400 kilometers per second, or 250 miles per second. As these particles travel further from the sun, they eventually collide with the interstellar medium. This collision creates a boundary known as the termination shock, where the solar wind abruptly slows down and heats up. Voyager 1 crossed the termination shock in 2004 at a distance of 94 astronomical units, which is roughly 14 billion kilometers, or 8.7 billion miles from the sun. Beyond the termination shock lies the heliosheath, a turbulent region where the solar wind is compressed and redirected by the pressure of interstellar space. The spacecraft spent 8 years traversing this chaotic zone, measuring the complex interactions between solar and interstellar plasmas. The ultimate boundary of our solar system's magnetic influence is the heliopause. This is the theoretical line where the outward pressure of the solar wind is perfectly balanced by the inward pressure of the interstellar medium. On August 25th, 2012, Voyager 1 made history by crossing the heliopause, becoming the first human-made object to enter interstellar space. The crossing was marked by a sudden and dramatic drop in the detection of solar particles, accompanied by a simultaneous increase in galactic cosmic rays. These cosmic rays are high-energy particles, originating from distant supernovae and other violent astrophysical events. Furthermore, the spacecraft's plasma wave instrument detected a significant increase in the density of the surrounding plasma. Inside the heliosphere, the plasma density was extremely low, but upon entering the interstellar medium, the density jumped by a factor of 40. This confirmed that Voyager 1 had indeed left the protective bubble of the sun and was now exposed to the raw environment of the galaxy. Voyager 2, the twin spacecraft, followed a different trajectory. It explored Jupiter, Saturn, Uranus, and Neptune before heading southward out of the ecliptic plane. Voyager 2 crossed the heliopause on November 5th, 2018, at a distance of 119 astronomical units, which is approximately 17.8 billion kilometers, or 11 billion miles from the sun. Because Voyager 2 carries a working plasma science experiment, which Voyager 1 does not, it provided the first direct measurements of the temperature and density of the interstellar plasma. The data revealed that the interstellar medium is significantly warmer than previously predicted, with temperatures reaching 30,000 to 50,000 degrees Kelvin. However, because the plasma is so incredibly sparse, it does not transfer significant heat to the spacecraft. The physical temperature of the probes remains bitterly cold, hovering around minus 225 degrees Celsius or minus 373 degrees Fahrenheit. The survival of these spacecraft in such extreme conditions is a testament to their robust engineering, particularly their power source. Both Voyagers are powered by radioisotope thermoelectric generators. These devices do not rely on solar panels, which would be entirely useless at such immense distances from the sun. Instead, They generate electricity from the heat produced by the natural radioactive decay of plutonium-238. This isotope has a half-life of 87.7 years, meaning that the heat output steadily decreases over time. Additionally, the thermocouples that convert this heat into electricity degrade due to constant exposure to radiation and extreme temperature fluctuations. As a result, the electrical power available to the spacecraft drops by about 4 watts every year. To keep the probes functioning, engineers at the Jet Propulsion Laboratory have had to execute a carefully planned sequence of instrument shutdowns, prioritizing the most critical scientific sensors. As the power supply dwindles, the mission will eventually transition from an active scientific endeavor to a silent, ballistic trajectory. By the late 2020s or early 2030s, both spacecraft will likely lack the power to operate any of their scientific instruments. Eventually, they will lose the ability to power their radio transmitters, severing the final link with Earth. From that moment on, they will become silent monuments to human curiosity, drifting endlessly through the cosmos. But their mission will not truly be over. Attached to the side of each spacecraft is a 12-inch gold-plated copper disc known as the Golden Record. This record is a time capsule, a message in a bottle cast into the cosmic ocean, designed to communicate the story of our world to any extraterrestrial intelligence that might intercept it in the deep future. The Golden Record was curated by a committee chaired by the late astronomer Carl Sagan. It contains 115 images encoded in analog form, representing the diversity of life and culture on Earth. These images include anatomical diagrams, photographs of nature, human architecture, and scenes of daily life. The record also features a variety of natural sounds, such as wind, rain, surf, and the calls of various animals. Furthermore, it includes musical selections from different cultures and eras, ranging from classical compositions by Bach and Beethoven to traditional folk music from around the globe. Spoken greetings are recorded in 55 different languages, beginning with Akkadian, one of the oldest known written languages, and ending with Wu, a modern Chinese dialect. The sheer breadth of information encoded on this disc is intended to provide a comprehensive snapshot of humanity at the moment of launch. To ensure that an alien civilization could understand the contents of the Golden Record, the committee developed a universal first contact protocol. The cover of the record features a series of diagrams etched into the gold plating, serving as an instruction manual for playback. The fundamental unit of time and distance used in these diagrams is based on the physical properties of the hydrogen atom, the most abundant element in the universe. Specifically, it uses the time it takes for a hydrogen atom to transition from one energy state to another, a process that emits a radio wave with a frequency of 1420 megahertz and a wavelength of 21 centimeters or 8.2 inches. By using this universal constant, the creators of the record provided a mathematical key that any advanced civilization should be able to decipher, regardless of their own systems of measurement. The cover also includes a diagram of the stylus and the record, indicating the correct rotational speed of 16 2/3 revolutions per minute. To help the finders locate the origin of the spacecraft, the cover features a pulsar map. This map displays the location of our sun relative to 14 specific pulsars, which are rapidly rotating neutron stars that emit regular pulses of electromagnetic radiation. Each line on the map represents the distance and direction to a specific pulsar, and the binary code along each line indicates the precise frequency of that pulsar's emissions. Because the rotation rate of a pulsar gradually slows down over millions of years, an advanced civilization could use this map not only to find our solar system, but also to calculate exactly when the spacecraft was launched. To provide an independent verification of the launch date, a small patch of ultra-pure uranium-238 was electroplated onto the record's cover. By measuring the radioactive decay of this isotope, which has a half-life of 4.5 billion years, the finders can determine the age of the record with remarkable precision. As the Voyagers carry this profound message outward, their immediate future involves a journey through the most distant and least understood region of our solar system, the Oort Cloud. The Oort Cloud is a theoretical spherical shell of icy planetesimals that surrounds the Sun, extending far beyond the orbits of the planets and the Kuiper Belt. It is believed to be the source of long-period comets that occasionally visit the inner solar system. The inner edge of the Oort Cloud is estimated to begin at a distance of roughly 2,000 astronomical units, which is about 300 billion kilometers or 186 billion miles from the Sun. Voyager 1, traveling at its current speed, will not reach the inner edge of the Oort Cloud for another 300 years. The sheer scale of this structure is difficult to comprehend, as its outer boundary may extend as far as 100,000 astronomical units, or nearly halfway to the nearest star. Transiting the Oort Cloud will be the longest phase of the Voyager's journey. It will take Voyager 1 approximately 30,000 years to pass through this vast field of icy debris. Despite the massive number of objects believed to populate the Oort Cloud, the space between them is so immense that the probability of a collision is infinitesimally small. The spacecraft will drift silently through the darkness, their trajectory slowly influenced by the faint gravitational pull of the distant sun and the occasional passing star. During this immense span of time, the probes will be subjected to the harsh realities of the interstellar environment. They will be bombarded by high-energy cosmic rays and slowly eroded by impacts with microscopic dust particles. However, because the density of the interstellar medium is so low, the physical structure of the spacecraft and the golden record itself are expected to survive for millions, if not billions, of years. Based on the latest trajectory simulations from the Jet Propulsion Laboratory, utilizing precise astrometric data from the European Space Agency's Gaia Observatory, we can predict the specific stellar encounters the Voyagers will experience in the deep future, in approximately 40,000 years. Voyager 1 will pass within 1.6 light years of a star known as Gliese 445. This star is an M-type main sequence red dwarf located in the constellation of Camelopardalis. Gliese 445 is currently moving rapidly toward our solar system, meaning that by the time Voyager 1 reaches its vicinity, the star will be much closer to Earth than it is today. Despite this relatively close encounter, Voyager 1 will not be captured by the star's gravity. It will simply fly past, continuing its endless orbit around the center of the Milky Way galaxy. Voyager 2 has its own distinct stellar destiny. In about 42,000 years, it will pass within 1.7 light years of a star called Ross 248, another red dwarf located in the constellation of Andromeda. Like Gliese 445, Ross 248 is also moving toward our solar system. Following this encounter, Voyager 2 will continue its journey, and in approximately 296,000 years, it will pass within 4.3 light years of Sirius, the brightest star in our night sky. Sirius is a binary star system consisting of a massive main sequence star and a dense white dwarf companion. The gravitational influence of these massive bodies will slightly alter Voyager 2's trajectory, but the spacecraft's immense velocity will ensure that it escapes their grasp, continuing its solitary voyage through the interstellar void. The ultimate fate of the Voyager probes is to become permanent residents of the Milky Way galaxy. Long after the sun has exhausted its nuclear fuel and expanded into a red giant, swallowing the inner planets and scorching the Earth, the Voyagers will still be traveling. They will orbit the galactic center every 225 million years, completing countless revolutions over the eons. They will pass through spiral arms, navigate the gravitational tides of giant molecular clouds, and witness the birth and death of countless stars. The golden record will remain intact, a silent testament to a civilization that once looked up at the night sky and dared to reach out into the dark. The first contact protocol will wait patiently, ready to be deciphered by any intelligence that might stumble upon these ancient artifacts. The Voyagers are no longer just spacecraft, they are interstellar monuments, carrying the legacy of humanity into the infinite expanse of deep time. Thank you so much for watching. Please subscribe and help me get to that 1,000 subscriber milestone.